Okay, since it is already 6:05, so maybe we can slowly begin. I'm already, I'm clearly visible, right? And this, audible, visible, and the screen is also visible, correct? Vinod, can you confirm once again? And can you also unmute and check whether I'm able to hear you or not? Hello. Vinod, are you there? Hello. Okay. All right. So, since everything is okay, maybe we can begin the session today. So, good evening, students. Welcome to week 5 of this problem solving session for analog circuit course. And I am the Sharda Devi, a PMRF fellow from IIT Gandhinagar. In today's session, we will be talking about stability. So, before we go into the problems, let's recall what we discussed last time. We discussed a little on stability last time already. So just let's recall once again, then we can go into the problems. Okay, for stability, we need to observe the S plane. In S plane, we have sigma and j omega excesses. So basically, real and imaginary excesses. And on this, so basically we all know that we obtain transfer functions, and those transfer functions gives us poles and zeros, and we are more concerned about poles than zeros. So yeah, talking about poles, so poles can be placed anywhere in this plane, on left hand side or right hand side, right? But what we understand is that this left hand side plane is stable. When the poles arrive in this left hand side plane, they are all stable. Okay, so this side of the plane is, all the poles on this side are stable, whereas excuse me, sorry, whereas the poles on the other side are all unstable. Yes, this side is unstable. So now when we talk about, say, we have a two pole system, and we want to know, okay, what will be the situation. Like in stability also, there are different kinds of stabilities, right? So when we talk about stability in general, what we mean by stability? Stability is, say in technical terms, when we give a bounded input and we get a bounded output, we say the system is stable. Now, for example, if you provide a step input, okay, so this is input. When you provide a step input to your system, okay. When you are providing a step input to your system, you can have different kinds of outputs possible, right? Ideally, what we want, let's say, if there is a step input, if my output can approach my input, then it is stable and also it is bounded. So, one thing that can happen is your output can slowly rise and it will meet your input towards the end. Then this system is stable. Correct. But there might be a condition that your output is slowly rising and it rises and goes to infinity as your time increases. Okay. This is, let's say, with respect to time. This is another type of situation that can occur. Correct. So, one thing is your output is being output is converging to your input. Another is output is not converging to the input and it's increasing, and as the time reaches, say at infinite time, your output will reach to infinity, right? So this particular configuration is a stable configuration because for a bounded input your output is bounded. Bounded means it has some limit. It is not going it is not increasing exponentially, right? So it has got some uh, limit. So that's why this is a stable system. Now, when we have this kind of behavior where our output is increasing significantly and at infinite time it becomes infinity, that is unbounded because the value is increasing drastically. So this we call as an unstable situation. Now, instability also, there are different kinds of possibilities. First of all, like as we have seen here in first case, let's say A. In first A case, when your uh, output is rising slowly and then it settles down, that is first situation, and we call it a damped system. Okay, and this is actually overly damped. So if I say, so the slower it rises, the more damping it has. Basically, that is the idea. The faster it rises, the damping factor is less. Okay, so yeah. So these are stable, but we also call them overdamped systems. Now, let's say what happens, your output is increasing and suddenly it overshoots. That means basically it goes beyond your input. But after some time, it comes down and it goes under the system. Okay? Under the input. And then slowly what happens is your amplitude starts reducing, and at some time it will become stable. Okay? So when we talk about system being stable, we talk about after a certain period of time. We don't talk about the immediate situation. Okay, after some time, when we see that, okay, what is the situation now? So after some time, what we observe is in these kind of systems, at the end, the output almost settles to the input. So that's why this is also a stable system. But what we call them is, we call them as damped system. These are damped. The previous one was over damped. This is damped system. So in overdamped system, if we talk about the poles, so if it is a two-pole system, then the poles will be real poles. In overdamped system, you will obtain two poles and both poles would be real in nature. So this particular system has real poles. Whereas when you have a damped system, so in damped system, uh, we will observe both real as well as imaginary parts in the poles. So basically, they will look like sigma plus minus j omega. So we will have conjugate poles, but with both real as well as imaginary part, right? And the third situation is what can happen is, let's say you observe this rise. So overshoot is there, then it comes down. But what if my amplitude does not go down and it stays at a limit? Right. So in this case, it is not completely settling at the input value, but it stays in a certain range, right? So these systems, we call them as marginally stable systems. We call them as marginally stable systems. And in real life, if we talk about how the poles will look like, so in this marginally stable system, the poles will be plus minus j omega. They will only have imaginary part. They will not have a real part. So because of this imaginary part, we will observe these oscillations. Okay. Now, another situation can be that the output is slowly rising. It overshoots, undershoots. But rather than damping, what happens is the amplitude of these oscillations starts increasing. Can you see? So this kind of behavior is actually possible in two-pole systems. And this behavior is unstable. So this particular system is unstable. And when will this system occur? When we have RHS poles, right-hand side poles. So irrespective of the pole position, whenever we will have right-hand side poles, we will observe this particular situation, right? So if I have to draw these on our plane, Yeah, if I have to draw these poles on the plane, so how they will look like? If we only have two real poles, that means they will both be appearing on x-axis, correct? So these are overdamped. These are overdamped poles. Now, when we have a damped system, what we said in damped system, we will have real as well as imaginary part. So there will be two poles, and how the imaginary part will appear, it will be like they will be in a conjugate situation. So they will have same x position but different y's, right? So this corresponds to a damped situation. Now third was marginally stable, right? So when we said marginally stable, see how the poles are. Poles will only appear in j omega axis. So if the poles only appear in j omega axis, the poles will only be in y axis, and this situation is for marginally stable, right? And in any other case, if we have poles in the right hand side, the system is unstable. Now it can be real poles, it can be any conjugate pair, but all these poles are unstable. Okay. Now when we talk about stability, then we need to understand that whether it is stable or not, we need to have certain measure, right, to identify these things. So we identify stability, or I should say we quantify stability based on two things: phase margin and gain margin, as we discussed it last time, correct? So phase margin is phase 180 minus phase, I should say. Phase margin is 180 degrees minus phase at omega 0 dBs. So when our gain reaches 0 dBs, whatever is the frequency, at that particular frequency, we will calculate the phase and we'll subtract it from 180. So whatever is the phase margin, it will tell us about the stability. Higher the phase margin, better the stability. Similarly, for gain margin is nothing but 1 by gain at omega 180 degrees. We would find the frequency at which the phase is 180 degrees, like it reaches minus 180 degrees. And at that particular phase, what is the minus 180 degrees. And we will, at that corresponding phase, what is the gain? We will take the inverse of that gain, 1 by gain, we'll get GM, right? So if I talk about this from our Bode plots, which we have understood quite well. So let's say this is frequency, and here we have phase, and here we have gain in dBs. Oh. This should be better. Okay. So let's say in this particular graph, I have my graph going like this. All right. So in this particular graph, and my phase somewhere, so this is say 0 degrees. I'm going down, 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 and here at some point, I reach say 180 degrees. Okay. So this particular frequency is omega 0 dBs. And at that particular frequency, this is omega 0 dBs. At that particular frequency, we'll calculate the phase. And that particular phase will correspond to our phase margin, theta. Okay, so this is theta. And now, at this particular phase, at this particular frequency, my phase is minus 180 degrees. Right? So corresponding to that, I'll have my omega 180 degrees. And at this frequency, we will calculate at this particular frequency, we'll calculate the gain and this particular gain, when we take 1 by, when we inverse this particular gain, we will get what is called the gain margin. Okay. So this is the idea of phase margin and gain margin. Based on these two factors, we determine the stability. Correct? Any doubts in this? We discussed this already, right? So let's quickly move on to the problems. So, okay, so the first problem is when you have in a system, if we have a negative phase margin and positive gain margin, then the system is stable or unstable. How do we define that? So first of all, we know that phase margin is 180 minus, or let's say plus theta, because it can take care of my phases sign. If my phase is negative, then it should not reach minus 180. If it reaches minus 180, my system will become unstable, correct? So I want my phase margin should be positive for stability. Similarly, I also want my gain margin to be positive for stability. So if we, so if say I have phase margin, gain margin, stable or unstable systems. Okay. And say my phase margin is positive, gain margin is positive, then the system becomes stable. Okay. If my phase margin is 0, gain margin is also 0, then system becomes marginally stable. That means the situation where our poles lie on the y-axis. Now, let's say if my phase margin is positive, gain margin is negative, then the system becomes unstable, and vice versa is also true. For a system to be stable, mind that both the phase margin and gain margin should meet the conditions. Otherwise, the system becomes, if any one of them does not satisfy the condition, then the system becomes unstable. And if both are negative, then the system is definitely unstable. So since it is given that it has a negative phase margin, then the system is unstable. Okay. So this was a straightforward question. Nothing very, like, it's not very complicated. So oscillatory basically means marginally stable systems only. So here we can also call them oscillatory systems. It basically means the same thing. So it is here, since in this problem it is mentioned oscillatory. So oscillatory means marginally stable system. Okay. Now question number 2. Question number 2 says, what is phase margin? Phase margin is, it is the amount of additional phase lag at the gain crossover frequency required to bring the system to the verge of instability. B, it is always positive for stable feedback systems. C, it is calculated at gain crossover frequency. And D is all of the above. So what is phase margin? What is the answer of this problem? Yes, students, what is the answer for this problem? What is the answer? A, B, C, or D? Come on. We discussed it already, right? Any doubts in the phase margin? See, when I say phase margin is 180 plus theta, and for example, my theta is minus 135 degrees. Then my phase margin is 45 degrees, right? Now, if I include theta plus 45, if I introduce a lag of 45 degrees, lag means negative angle, right? So theta minus 45 degrees as theta dash, then what is my new phase margin? So theta dash is how much? Minus 135 minus 45 degrees. This will become 180 degrees minus, right? So phase margin will be 0. So that means it basically gives us the limit of additional phase lag required at the gain crossover frequency to bring the system into instability, right? So that's why this option is correct. We already mentioned in the previous problem that it is always positive for a stable feedback system. And also it is calculated at gain crossover frequency. So the answer is all of the above. Any doubts in this? Hope there are no doubts. If you have any doubt, feel free to unmute yourself and ask. Okay? Since I didn't receive any response, so I consider it as no doubts. Okay, so moving ahead. In this problem, so it is given that what is the value of gain margin in second order system?
Why you are taking two times?
Sorry?
Why are you taking after getting phase margin 45 degrees? Again, you are
Yes.
doing 180 minus 180. Why?
Yeah. So that's just to show that if we introduce the phase margin, just gives a value of phase, right? So basically, if we introduce the same amount of phase, in lagging situation, then we will go into instability, right? So it basically satisfies the first problem. So what is phase margin? It is the amount of additional phase lag at the gain crossover frequency that is required to bring the system to the verge of instability, correct?
Yes.
To satisfy that statement, I showed you this.
But now we have 45 degrees phase
Yeah,
margin.
so 45 degrees is the phase margin. So we are left with a margin of 45 degrees. If 45 degrees lag is introduced in the system will become unstable. So phase margin gives us that idea of how much limit we have. What is the limit that we have to make the system unstable?
So if you have 45-degree lag, then it becomes unstable.
Yes, that is the idea of phase margin.
But now we have plus 45, so stable.
Where stable?
It is stable, no, ma'am?
No, no, B is unstable. The situation
No.
is unstable, right? When phase margin reaches zero or it becomes less than zero.
Okay, if it is 45, it is stable.
Yes, phase margin is 45, this is stable.
Huh.
But so this is condition one, then in condition two, the phase margin becomes zero. That is unstable.
Okay.
And the limit to that was 45 degrees. So which was basically the phase margin initially, right?
Okay.
Yeah, so just to show that first statement, how you can interpret the first statement, I showed you this calculation.
Okay. Thank
Okay, yeah.
you. Okay.
So moving on to the second problem. So in in the next problem, in this problem it says what is the value of gain margin in second order system? Will it be unity, zero, infinity, or constant? So what is the idea? First of all, gain margin was 1 by gain at minus 180 degrees. So if you have reached minus 180 degrees already, then what is the gain that you have? So in second order system, there are two things that are possible. Like if you have a second order system and phase has already reached to minus 180 degrees. So how will your second order system look like? It is A upon S plus A and say S plus A and S plus B, correct? This is a two pole system. Two poles means second order system, right? And if your phase has already reached 180 degrees, that means both of your poles are contributing to minus 90 degrees each, right? Which is the maximum a pole can introduce. Maximum phase a pole can introduce. So if I write the phase of your transfer function, how will the phase look like? Minus tan inverse omega upon A minus tan inverse omega by B, and this is minus 180 degrees. So let's say these two are almost like if we share them equally, and one particular phase, one particular uh, pole introduces a 90 degrees and another one again introduces a 90 degrees, that basically shows that omega is infinity, right? Similar behavior will be observed for the other pole also. So when omega is infinite, at that particular time, your if here say I substitute omega equal to infinite, my mod g will become 0. And if my mod g will become 0, my gm is 1 by g. So this becomes infinity. So that's why in two-pole system, if we like reach the 180-degree phase, minus 180-degree phase, that means that will only happen when you reach the infinite frequency, right? So the gain margin for a second order system is infinity. Like first order system will also first order system will also not see the problem with gain margin and the phase margin both. So first order systems don't have the issue of gain margin and phase margin, because we know that in first order the maximum phase that can be obtained is minus 90 degrees, which will again come for omega equal to infinity, and that is like at the infinity only. So phase margin will also come, like margin is also infinity, and gain margin is also like 90 degrees that we have. And in second order, we can reach 180 degrees, but at the limit that when omega tends to infinity. But what about third order? If the situation is third order, that means in third order you have to you will have uh, three poles, and you need to reach a phase of 180 degrees, minus 180 degrees. That is quite easy, right? If I say all three poles are overlapping poles, like one over other, then I only need to introduce 60 degrees, right? 60 degrees from a pole, and I can attain that minus 180 degrees limit, which is quite easy. And the omega value will also come in a significant range. And as we start increasing our orders from say third order to fourth order to fifth order to nth order, our gain margin starts taking a toll. So basically phase margin and gain margin starts reducing as you start increasing the order of poles, and it leads to the chances of instability. That's why higher the order, more are the chances of instability. A single order system will never be unstable. No matter what frequency you run your system will never be unstable. In second order you have some chances, but that too it's not like that too at very high frequencies, like almost infinite frequencies. So it's very high frequencies. But beyond that, as you start increasing the orders of the systems, be it your filters, your amplifiers, whatever circuit you have, if the order goes beyond a second order and it's as it starts increasing, the system starts becoming unstable. So you need to take measures to make your system stable. So there are different techniques to make systems stable, but yeah, so those techniques are used. But as we start increasing the order of the system, the system becomes more prone to instability. Okay. So yeah, moving
Why,
on to
why one
yes.
pole means minus 90?
Sorry.
Pole means minus 90.
For pole it is minus 90, right? Pole. So if it is like, how do you write? So this is the maximum. I am saying the maximum angle that a pole can introduce. Tan inverse infinity. Infinity can be the maximum value, right? If I say a upon s plus a, say this is my transfer function g, then the angle of transfer function is minus tan inverse omega by a, correct? Right?
Yes, yes, yes.
And omega by a can take a maximum value of how much? Infinity,
Uh,
right?
uh,
Can you go beyond infinity? There is nothing beyond infinity, right?
yes.
If 2 times infinity is also infinity, infinity into infinity is also infinity. So anything into infinity plus minus infinity is always infinity. So that's why infinity is the maximum that you can attain. Now when I substitute this, so my angle becomes minus 90 degrees, right? So this is the maximum that a pole can introduce. You cannot go beyond that. Okay. So that's why I wrote down, like, when minus 180 was introduced. So I said that since maximum a pole can introduce 90 degrees, so there is a possibility that both the poles will provide 90 degrees each, but 90 degrees will be attained only at a cost of the omega being infinity, because there is no other way, right? How can you make this omega by a as infinity? Either omega tends to infinity or a tends to 0, but a is already fixed, right? So there is a only situation that omega can tend to infinity. Then only your w by a will become, or omega by a will become infinity, right?
Okay, ma'am. Okay.
Yeah, so from there, okay. Okay. So moving on to the next problem. So in this problem, it is said that open loop transfer function of unity feedback control system. Unity feedback control system is given by GS is S plus 1 by S square. The gain margin of system is how much? So the open loop transfer function of the system is this. This is open loop transfer function. And we have to find the gain margin for the system. So for finding gain margin, we need to find omega minus 180 degrees, because minus 180 degrees is the limit. So if we start finding the gain for this OLT, open loop transfer function, and since it is a unity feedback control system, so if it is a unity feedback control system, then closed loop transfer function becomes a upon 1 plus a beta. Then unity feedback means beta is 1. So a upon 1 plus a. So if we write it like this, s square. So this is s plus 1 by s plus 1 plus s square, right? So if this is the closed loop transfer function, so first we can comment based on open loop transfer function also, but since it is already a feedback system, so better to analyze the closed loop system as well for the final answer. So closed loop transfer function. So if it is s square plus s plus 1, so what will be the factors? What will be the factors for this? So this becomes minus 1 plus minus root 3j. So these are the poles of the system. Okay. So we have two poles and 1 0. So the transfer function will look like transfer function is s plus 1 by s. Okay, if this is the closed loop transfer function, and we have omega as the like phase we want is minus 180 degrees. So minus 180 degrees needs to be attained with the tan inverse omega. This is from the 0, then minus tan inverse omega by 1 by 2 plus root 3 by 2j, and minus tan inverse omega by minus 1 by 2 minus root 3 by 2j. So from here, what we will obtain is the omega for the closed loop transfer function, which will give us minus 180 degrees. Okay. And if we go ahead with this g, which was already given, that was our open loop transfer function. And for that, the angle becomes omega open loop transfer function. It is minus tan inverse omega minus 180 degrees. And since here we already have minus 180 degrees as our limit, and minus tan inverse omega and minus 180 degrees. So if these two cancel, then omega becomes 0. So this we get from open loop transfer function. From open loop transfer function, when we try to find the gain margin using open loop transfer function, we obtain our omega as 0. Because if our open loop transfer function, so first of all, the moment we introduce feedback, we know that it increases the stability of the system. And if we already have a open loop system, so first we start to analyze like the open loop system's stability, and then we can comment on the given phase margin and gain margin, because anyways when we introduce the um, feedback, we will get the stability in the system. Like here, if we observe that while calculating the phase for open loop transfer function, we got our theta or our frequency to be 0, right? And now if we start to calculate the gain margin becomes 1 by mod g, that is 1 by root under omega square plus 1 by omega square. So which is 1 by root under 1 by omega square plus 1 by omega to the power 4. So when I substitute 0 in this, I'll get my gain margin as 0. So here what I get my gain margin as 0. So this comes from the omega that we calculated from open loop transfer function. And in open loop transfer function, if we have found the omega as, gain margin as 0, then in closed loop transfer function, definitely the gain margin will improve. So if we try to solve this, it's a bit tricky to solve, but if we solve this, we can clearly observe that whatever the omega that will be observed for a closed loop transfer function, it will improve our gain margin, and we'll get value for gain margin rather than finding gain margin as 0. Okay, so now it is given that we have to calculate the gain margin for in dBs for open loop transfer function. Again, it's an open loop transfer function with G and H as 1 upon S plus 2. So first we need to write the phase. So phase will be minus 90 degrees from the S, and then we'll have minus tan inverse omega by 2, and this I need to be needed to be minus 180 degrees, minus 90 minus tan inverse omega by 2. These two cancel. We have minus 90 degrees as minus tan inverse omega by 2. So omega turns out to be infinity, omega minus 180 degrees. Now when omega turns out to be infinity, then for gain margin we need to find the magnitude. So that is omega root under omega square plus 4, and substituting infinity in this, we'll get mod omega as 0. Then gain margin is 1 by mod g, that is 1 by 0, which is infinity. So here the gain margin that we obtain is infinity. Okay. So first of all, analyzing an open loop transfer function is much easier compared to analyzing a closed loop transfer function, as we have already seen in the previous problem. And if your open loop transfer function is already stable, then closed loop transfer function will definitely be stable. And if open loop transfer function is unstable, then we can see like how much is the limit that we need and all. So that's where we start calculating these gain margins. Okay. Now coming to the next problem. So in this problem, it says if the gain of the open loop system is doubled, then the gain margin will be. So we have seen that if the gain is doubled, G dash is twice of G, and we know gain margin is 1 by the gain, right? So the gain margin will be how much? It will be halved, right? Twice of G. So which is basically GM, this is GM dash. So GM dash is GM by 2. So gain margin will be half. Half of the earlier situation. If gain is double, gain margin will become half as they are inversely proportional. Now coming to the next problem. So in this problem, an amplifier with resistive negative feedback has two left plane poles in its open loop transfer function. The amplifier will be unstable at high frequencies, will be stable at high frequencies, may be unstable depending on the feedback factor, and will oscillate at low frequencies. So, okay, so the idea is that first of all, the feedback is resistive in nature. When a feedback is resistive in nature, that means A beta is what we consider, right? With the feedback factor, where beta is feedback factor. And if beta is resistive, then if beta is resistive, that means it is constant in nature. It will give us a constant value. We will not obtain any frequency dependent parameter. Okay. So if we don't observe any frequency dependent parameter, then we can simply compare. So based on this S plane that we discussed right in the beginning. So based on this S plane, since um, the system is the feedback is resistive in nature, so it will not increase the number of poles, or it will not introduce a new pole. Here also, if
It's
you
stable
observe,
system.
yes, so based on that, it is stable system. But if we see like here in this unity feedback, also unity feedback means beta is 1, right? But if it was a resistor feedback, then beta would be some k, but it is also a constant value. So if you see from the open loop system, it was a two pole system, correct? Open loop system was a two pole system. Now, if we look at the closed loop system, it is also a system, correct? So, if you have a resistive feedback, that means the number of poles are not going to change. It's just the pole placement will change, but number of poles remain the same. Okay, so that's why in case of resistive feedback, we can analyze the open loop transfer function itself and comment on the gain margin or phase margins. We don't need to go to the closed loop system, because we know that the number of poles and zeros introduced to the system will remain the same. It's just that placement will change a little. Okay, so that's why uh, so here, since it is resistive, so it will be a constant. And then if the two poles are in the left hand side of the plane, then the system is stable for all the frequencies. Okay, right. Now moving on to the next problem. So in this problem, we have the phase margin of a system has an open loop transfer function of 2 root 3 s plus 1. 2 root 3 s plus 1. Then we need to find the phase margin. So for phase margin, what is required? What do we need to calculate first for phase margin? Or let's move from backwards, okay? For phase margin, what is required? What is phase margin? How do we calculate phase margin? Yes, anybody? How do we calculate phase margin? Yes. So it is 180, say plus theta. plus theta because I can like see the actual behavior of the angle, like sine of the angle. Okay, so that's why I wrote it as plus theta. Now 180 plus theta crossover. So crossover frequency means crossover frequency needs to be the frequency at which omega crossover. Omega crossover means mod G is 0 dBs. So for that, first of all, we need to calculate the magnitude, right? What will be the magnitude of this particular transfer function? 2 root 3 omega square root under omega square plus 1, right? So if 2 root 3 it should be 0 dB or 1 volt by volt, say it, if it is volt by volt, or if no unit is there, then let's say it is 1. So this should be 1. So that means 2 root 3 equal to omega square root under omega square. Oh, this is not omega square, this is omega, right? Omega and root under omega square plus 1. So what will be the value of omega from here? Yes, what will be the omega? Let's do squaring on both sides. So this is 4 into 3 omega square into omega square plus 1. So this is 12 equal to omega to the power 4 plus omega square. Yes, what is the value of omega? How do we solve this? Omega to the power 4 and omega square. How do we solve this kind of equations? Anyone? Anyone? How do we solve these kind of equations like omega to the power 4, omega square? So one of the easier ways is, let us assume omega square as say x. Okay. Then we can simply write it as x square plus x minus 12 equal to 0. Sorry, you are getting omega as 1.73. Okay. So if we do it this way, then it is x square plus x minus 12 is 0. Now let's find the roots to the quadratic equation, that is minus b plus minus root under b square minus 4ac by 2a. So this will be minus 1 plus minus b square 1 minus 4 a into c, so 12 by 2. So the roots are, this will give us two roots. One is minus 1 plus minus 1 plus root under 49 by 2 and minus 1 minus root 49 by 2. So that is minus 1 plus 7 by 2, which is 6. No, 6 by 2, 3. And here it is minus 1 minus 7 by 2, that is minus 4. Now see, omega square is x. This is the value of x, right? Now can omega square become minus 4? Yes, we got two roots, right? One is 3, another is minus 4. Can we have omega square as minus 4? Would you have omega 3 as, omega square as minus 4? Is it even possible to have any square value as negative? Unless it is an imaginary number, you cannot have a whole square as negative, right? And frequency is a real value. So real value cannot take imaginary numbers. So that's why x is 3. So if x is 3, this is also omega square. That means omega is 1.5. Now here also we will have plus minus, but minus of frequency does not make a sense. So that's why omega is 1.5. So the crossover frequency, omega crossover frequency is 1.5 radians. If omega crossover frequency is 1.5 radian per second, then the next thing that we need to calculate is phase of the system. So phase, how do we write the phase of the system? It is minus 90 because of S, and because of S square we will have tan inverse omega by 1. So this is minus 90 degrees minus tan inverse 1.5. So what is the angle that you obtain over here? Yes, what is the angle that you are getting over here by substituting? Oh, wait. ये क्या कर दिया? This is not by 2, right? Nobody pointed this out. This is root under. So this is root 3, correct? This is root 3. Yeah. So tan root 3. How much is tan root 3? How much is tan root 3? What is the value? Tan inverse root 3. What is the value? Yes, it is 60 degrees. So this is minus 90 minus 60. So we are already at minus 150 degrees. This is the angle at omega crossover. Now we will find the phase margin. So phase margin is 180 plus angle GH of S omega crossover. So the phase margin is 180 minus 150 degrees. Phase margin comes out. Hello. Am I audible clearly? Hello.
Yes, ma'am. Audible.
Okay. So, did you people lose the connection? Was my screen off for any time? Like, I did not realize. I just got.
Momentarily, audio was not there.
Oh, audio was not there. Acha. So, did you people understand this solution? Like, how we moved step by step in this problem? How we reached till phase margin? Did you understand every step? Any doubts in any step?
No,
At least
madam.
where
Yes,
the audio
you
was
understand.
off. Is it clear?
Yeah, clear, madam. Clear.
Okay, so if it is clear, maybe we can move to the next problem. So in this problem, it is asked that which of the following causes change in gain and introduces a phase shift? Internally integrated resistor, internally integrated capacitors, internally integrated inductors, or is it both internally integrated capacitors and inductors? What is your take on this?
B and C, madam.
Okay, so why? You're saying this option, right? Can you explain why?
Madam, what I feel is inductors and capacitors are frequency selective devices compared to resistor.
Right,
They depends on the frequency.
right. But see,
So
okay, so you are saying since they are frequency selective devices, so they can introduce phase shifts and
yeah,
as well as change in gain. But what is the meaning of internally integrated?
it is fabricated on single silicon wafer. It is grown
Okay.
on the wafer.
Okay. So here, basically, the idea is when we say internally integrated, it's actually the capacitance and inductance which appears naturally while designing the circuits. Okay. And since we are not dealing with um, magnetic fields, so we don't usually observe like any sort of inductance effect in our devices. But when we talk about our devices, like the most prominent device that you use is either a BJT or a MOSFET, correct? For designing any circuit, any filter, or any analog circuit. So these devices have their intrinsic capacitors formed at the junction and also, yeah, across the junction, and in MOSFETs you have gate capacitance also. So these capacitors are present and they are already observed. So they are there, their effect is there. But inductive effect has never been
Doesn't come
observed.
into picture. Isn't it?
Sorry?
Inductors doesn't come into picture.
Yes, inductance doesn't come into picture because we are not dealing with magnetic fields, right? For inductance effect, you need magnetic field.
Okay.
And since we are not dealing with magnetic field, so that's why inductance is never observed. So that's why we always try to replicate our devices or circuits with RC networks. We never say it is RLC network. We always say it is an RC network. Even while calculating delays and other analysis, we always go for R and C. We only consider the two factors, resistive and capacitive factors. We never introduce inductive influence into it because we are not working with magnetic field. So inductance effect will not be observed unless you start using magnetic fields and then you see some difference, right? So that's why
Okay.
internally
Clear.
integrated, yes, so that's why internally integrated component will be capacitors. And because of these internally integrated capacitors, other than the capacitors that you use in the circuit, you will see certain fluctuation in gain as well as in the phase shift. And those shifts are basically observed because of these stray capacitors, or we can say the junction capacitor, or we can say um, the parasitic capacitors that come into picture due to the device as well as the connections itself. Okay, so that's why the effect is, so if it was externally like if the components are being externally connected, then if we connect an inductor or a capacitor, we will see certain behaviors. We will definitely see gain and phase shift change if we are connecting these components externally. But since it is internally integrated components that we are talking about, so in internal integration, so basically while fabrication of devices, You never observe an inductive effect over there. So that's why we are only considering the internally integrated capacitive effect. Is this clear? So this is the physical characteristics. This happens because of the physical characteristics of the device itself due to the semiconductor device that is used. Okay? Any doubts in this? Okay, so the problems which I selected for today are finished at this point. So if you have any doubts, feel free to ask. Any doubts, anything that you want to discuss? Any doubts that you people have? Feel free to discuss. Any problem, anything that you people don't understand? Any concept that you want me to discuss?
Ma'am, here in this problem,
This problem? Huh.
yes,
Okay.
how did you write that step CTL is equal to S plus 1 by down?
Oh,
down.
this is so CTL is closed loop transfer function.
After that, after getting poles,
After getting?
minus 1 by 2 plus root 3. After that, S plus 1 by S plus minus 1 by 2, that one.
Oh, so I just wrote it like if we have two roots, the roots are already known to us, then I can, so if I have say s square plus s plus as plus b, it gives me two roots, say c and d, then I can write this as s plus c into s plus d, right? If I multiply this, I'll get this equation, right? Similar equation, correct? It's like, okay, for example, say s plus 2 into s plus 3. Okay? So if we start expanding, how it will look like? Correct? So this is s square plus 5s plus 3. Right? So what are the roots? S equal to 2 and s equal to 3. So I can write it like this again, right? So I just, do you understand? These are interchangeable.
Okay.
So it's in the same way when we found the roots, I just wrote it as s equal to, so this is, what is this? This is s equal to the roots, right? This is the value of s that we solved the roots for. So if I know the roots, I can simply write it, no? Or I should be, okay, so if it is s equal to, so maybe I should write minus here. Yeah, this should be minus. So there will be slight change in the angles also, because it is, if it is minus, then a minus b. So it will be 180 minus theta. So or 90 plus theta. So it is minus 90 plus theta, and here also it will come out to be minus 90 plus theta. This and this cancels this and we'll get 0. So again from here also, since it is 0, so things will go down to more or less 0. Yeah, but anyways, so here, yeah, so if it is s equal to this, now s equal to, here it will be minus 2 and minus 3. So that's why it becomes s plus 2 and s plus 3. Like, so if we start breaking this down, how it will look like? Minus b plus minus b square minus 4 AC by 2. This is S. So S equal to minus 5 root over 25 minus 12. By 2. Where is it going wrong? Oh, this is 6, right? Silly mistakes. Yeah, yeah. So this is 6. That's what I'm thinking. Why is it coming out to be wrong? Now this makes sense. So this is 6. So 4, 6, 24. Here you will get 1. And because of that, S comes out to be minus 5 plus 1 by 2, or minus 5 minus 1 by 2. So here we'll get S as minus 2 or minus 3. So since S is minus 2 or minus 3, then S plus 2 equal to 0 or S plus 3 equal to 0. So these are the two factors. So that's how you go back. So here, rather than writing plus, I should have written minus. And if it is minus, then the values, like the phase values, will change depending on the trigonometric thing, right? Like where that, so it's like this. So when we have this xy plane, so like here all are positive. So tan inverse, you can directly write theta. But when here it is angle, so whether you are considering this theta or this theta, that will depend on the way you represent it. So based on that, your things change. So that is the idea. So it is either 90 plus theta or 180 minus the theta. And in that way, your tan inverse changes. So it's just what we call uh, this is in the algebra of imaginary numbers, right? Or complex numbers algebra, like when we try to find the angle for a complex number, there it will be like, so if say I have a plus ib, a minus ib minus a plus ib minus a minus ib, so all these are not corresponding to tan inverse b by a. Okay, so there will be tan inverse b by a, but along with that we will have some values. Like for this, the angle becomes tan inverse b by a. Okay, for this it will be -90 plus tan inverse b by a. And say in this, this is minus tan inverse B by A. Okay, so likewise things change. So this comes from trigonometry, and based on that, so that's why while writing the phase, we need to be a little careful to realize uh, in which phase it is. So according to that, the formula changes, and according to that, the additional values will come. Sorry, somebody's saying something. Was somebody saying something? So yeah, that's what I mean. So based on this, the things will change, right? So we need to be a little careful while writing the phase. That's what I meant. Any other doubts? Week 4 questions. Last week questions, do you want me to discuss that? Any question? Can you unmute yourself and ask? It is very difficult to understand while chat. Hello. Yes, somebody was saying week 4 questions. Can you please unmute yourself and ask what was the doubt? Any positive or negative feedback? Chandni, are you there? Can you unmute yourself? I'm not really sure what you're trying to ask. Can you unmute yourself and ask me?
Ma'am, after question number 5, it is in many signs in op-amp in negative feedback. So just I want to clarification about that those questions. So how to decide sign in negative or positive feedback op-amp?
Okay, so the idea is, see, your op-amp is this triangular box, right? Your op-amp is this triangular box, and you will have two input terminals. One, it will be written as negative, other it will be written as positive. Okay, if your output connects to positive, then this is positive feedback. Output connects to positive terminal of input. Okay, if this output connects to negative terminal of input, then this is negative feedback. So based on this, we decide whether the feedback is positive or negative. Is this clear? Was this the doubt or something else you want to ask? Was this the doubt? Chandni, right? I don't know. I guess you have joined with some other account. But anyways, this is the doubt, right? Or anything else that you want to ask? If you can confirm. Hello. But in question, MOSFET is also present. Okay, so what is the concern with if MOSFET is present, then what is the issue? Like, can you bring up the questions? Like, can you people also share your screens? Is it possible? I mean, I'm not sure. Can you share your screen? Can you share that question with me? So I can look at it and then comment. Because without looking at the circuit, I don't think I'll be able to comment. You can share your screen, I guess. Okay. So, meanwhile, is there anybody who has any other doubts? Anything that you want to ask me? Any concepts, anything that you want to discuss, any problem that you want to discuss? No doubts? Okay, so if there are no doubts, maybe we can break over here and we can meet next week with new set of problems and concepts. So that's all for today. If you have any doubts, please stay back and ask. Else you can leave the class. Yeah, thank you. Thank you for joining. Mr. Deshmukh, do you have any doubts? Mr. or Ms. Deshmukh, I'm not very sure. Are there any doubts? Hello. Hello, am I audible? R.D. Deshmukh ji, who's this? Am I audible? Is there any doubt that you want to ask? Okay. I think there are no doubts. So that's all for today. Thank you everyone for joining. See you all next week with a new set of problems and new set of concepts. That's all for today. Bye.